In this class, we're going to consider algebraic expressions. And the goal of this class is really to get down some of the terminology or the language that you'll need to know about algebraic expressions to use algebra going forward. So that when your teacher or someone like me is describing algebraic objects using certain terminology, you'll know what I'm talking about. So let's just have a look at these examples to help us sort of tease out some of that terminology and get the sort of common language that we can use going forward. So the first thing is that algebraic expressions are made up from terms. Each term in an algebraic expression has got a particular purpose. Some algebraic expressions only contain one term, some contain multiple terms. It's common to see algebraic expressions with 2 or 3 terms, 4 terms. There's special types of algebraic expression, which you'll learn about later, which are kind of determined by the number of terms that they've got in them, but you're going to see all sorts, but they're made up from terms. So this expression here has got 2 terms, 1, 2. This has got 2, this has only got 1, this has got 3, this has got 2. And the way you can tell is because of the operations plus or minus in between. So that will always exist between the terms. Okay, so let's just start with the first example here. So we know we've got 2 terms. What are some of the other features? Well, the x is the variable. So I think you should already be familiar with the idea of a variable from previous classes in this series. But let's just put down some of the terminology here. So the x is a variable. That's the thing in this expression, this algebraic expression, which is allowed to vary. So that means that this term is a variable term, because if x can vary, then 3x, and it's 3x, which is the whole term, that 3x term will vary as well. So as the x changes, 3x changes. 3x, remember, means 3 times x, okay? So when you write something like 3x or 3b, that means 3 times that letter. Okay, so that's the first term. The number that goes in front of a variable, which is not a variable itself, because 3 will never change regardless of what x value you put into this algebraic expression. The 3 itself will never change. The 3 therefore is described, it's not what it's called, but it's described as being constant. Sometimes it is referred to as the constant or a constant. It is a constant value. The 8 is also constant, it will never change. The term constant has got special meaning sometimes in mathematics, and we use it in various contexts, but here we're just going to use it for things which are not variable. So that kind of gives us a couple of categories. Terms in an expression can either be variable or constant. Constant are simply the things that will never change. Variables are by definition things which can vary. But the number that goes in front of a variable has also got another name, and it's called the coefficient. That's a really important term. You will hear that a whole bunch in the future. So your math teacher will often refer to the coefficient. So the coefficient here of the a squared term is 4. The coefficient of the 3b term, the b term, is 3. The coefficient here of the x squared term is minus 4. It's a number that goes in front of a variable term. Okay, so that's some of the important sort of initial pieces of terminology, I guess. Looking at this example here and comparing it to this one here, notice here we have the x term first, the term that contained the variable, then the number term. That is ideally what we would always go for, the variable, then the numbers. Notice here we go variable, variable, and then number. We'll talk a bit more about this one later. Why have we spun it around this time? Well, if we did put the number term, the 7, on the end, our expression would have to look like this. It would be minus 4x squared, because remember, this is not a 4, this is a minus 4. So that's really important. The sign, the plus or the minus, is important. So this minus 4 is a coefficient of the x squared, so that has to go like that. The 7 is a positive, so that would be plus 7. So that is a way we could write it that way, but there's a mathematical convention. It's a little bit like grammar, I guess. It's like math grammar, which says that if you've got the opportunity to not have the negative on the left of your expression, sometimes we call it hanging out the left-hand side. It's just a little bit ugly, we don't like it. There's a convention against it, so we usually spin it around. So if you ever saw something like that, you might want to take another line of work in to rewrite it like that. These are the same thing. These mean the same thing. These are equal. The important thing is the 7 here is positive and it's positive there. The minus 4x squared here is still a minus 4x squared and it's the same here. These are equal. We just prefer this one than this one. It's not wrong. It wouldn't be marked down, but it's just, we just don't like it. It's a kind of weirdness in mathematics. So that's just to highlight that point there. If you see your teacher correcting this working and turning it into this working, that's why. Just because we don't like negatives on the left. If you can't avoid it, if both terms were negative, if for example we had negative 7 minus 4x squared, then there's nothing we can do there. We can't spin them around because then they would still both be negative. So that would be perfectly acceptable in that case, and you will see that sort of scenario as well. Okay, let's look at a few other things to be aware of. So sometimes in an algebraic expression you will see special letters, particularly Greek letters. So here's the Greek letter pi. We know pi represents a special number. It's a number that appears in all sorts of mathematical objects. It's approximately 3.14, written to just 2 decimal places, but sometimes you'll see numbers like pi in a mathematical or algebraic expression, and they're just there because they've got some kind of special meaning. Another number you'll see in the future is the number e. So you could have an expression that says something like 2e plus 7. E is just another number. It's equal to 2.57, I think. 2.57, blah, blah, blah. It's another number that goes on and on forever. Something like that, maybe 2.56. I don't know, I'll need to check that one. I should really know that. Anyway, so you'll see these special numbers sometimes in mathematical expressions, but one thing to notice here, pi and e, even though they're written using letters, e obviously is from the English language, pi is from the Greek alphabet, but even though these are written as letters, they're not variables. These are constants, these are numbers, but they're special numbers. So these will never change. Pi will never be some number other than 3.14. E will never not be 2.5. I think it's actually 2.567, maybe, possibly. Anyway, they will never change. So in this expression here, x is the only variable. In this expression here, there are no variables, okay? Because e is actually just a number. So a little bit of nuance there, but you'll get used to it over time. It's just about experience. In the next expression, we've got sine theta. This theta is also a Greek letter. So theta is often used to represent angles. Not always, doesn't have to be, but if you see the letter theta, it will often be used in that position because it is an angle. And you don't know probably, or maybe you do have some experience already with the sine function from trigonometry. If you do, you'll know that this is to do with angle, so that's why theta gets used here, but it doesn't have to be. You will see also in many other scenarios just sine x, and that's perfectly fine as well. So in this case, theta is a variable, but it's a variable that represents an angle, so we might use x, but a lot of the time we'll use a letter which not only tells you it's a variable, but also says it's a variable and an angle. Okay, so that's why we're using it in that context. Okay, and then finally our example here, it's got 3 terms in this expression. So 4 is the coefficient of the a squared term. There's a second variable here, b. A and b are unconnected. And then you've got 3 is the coefficient of the second term to give you 3b. And then the constant term minus 13 on the end. So you'll see all sorts of expressions. They can contain 3 terms, 4 terms, whatever. It just depends on the particular question. So these are just some of the important definitions and terminologies to get down at this point, but you're going to end up seeing so many different types of algebraic expression that really experience as well as knowing the actual definitions is going to be important. But what I would recommend at this point is to try and get these definitions down by every time you see a mathematical expression and you have to work with it, just say to yourself, right, what is the 3? Oh yeah, it's a coefficient, and it's also a constant. What is the 8? Yeah, it's just a constant. What is the 3? It's a variable. How many terms are in this expression? Just by kind of going through that mental process a few times, you'll start to pin down what the terminology is. You're never, or it's unlikely at least, you're ever going to see a question which says something like, identify the coefficient in this expression. Your teacher might do that as an introductory way of working with algebraic expressions, but usually this is going to be assumed knowledge, or at least very quickly it will become assumed knowledge. So if you don't get the terms down now, it does just make it more difficult when your teacher's going on about some object, some mathematical object, some question, some equation or something on the board, and they're working through the question and they're using terms like the coefficient or the variable, and you're not quite sure what they mean. It makes it doubly difficult to follow the problem, right? So that's why we need to get this terminology down now. So this idea of algebraic expressions, learn the terminology. Remember, algebraic expressions are made up from terms, and terms are constructed using these terms here.